So, hi everybody. My name is Mark Brown. I am a principal program manager on the Cosmos DB team, and I'm going to talk about building high-performance distributed applications with Cosmos DB. So, just a level set. There's a couple of things I want you to walk away with in terms of what you're going to learn in this session. But fundamentally, the thing I want you to understand clearly and just internally in your mind is this relationship between consistency, availability, and latency when building distributed applications. So just kind of a show of hand, who's built applications that have had to run in kind of a distributed fashion over continents or even across countries? So, okay, so there's challenges in those things. And we're going to talk about kind of the relationship between these three things because they're super important to understand. So just to get started, so just to ask a question, why would you build an application that's globally distributed? And there's a number of reasons for this. So I'm going to pick on retailers for this talk, and I want to talk about availability, because availability is one of those reasons why you would build a distributed application. So in Thanksgiving 2018 was the start of actually the biggest shopping season ever on the planet. So within the US, on Thanksgiving Day, there was $3.7 billion of online retail sales. Not to be outdone, Black Friday, that following day, was $6.2 billion of online retail sales. And then, of course, the following Monday, Cyber Monday, nearly $8 billion of sales occurred online for retailers. So breaking that down, that's $91,000 a second, or $5.5 million a minute, or $329 million an hour. So if you're an online retailer, you're basically your entire year is make or break over this period of 3 days. The problem is that retailers, even experienced ones, tend to have issues with availability for their applications. And even this one famous retailer, now I'm not going to point out exactly who, so I've kind of blurred out their stuff here, so I hope you don't recognize who this is. But on their, I'll call this their Primo Day in 2018, suffered an outage that lasted for roughly 75 minutes. If I'm not mistaken, that cost them about $90 million. So $1.2 million a minute is what that cost them because their site wasn't available. But these don't just apply to online sales and revenue. Retailers or customers in general, or excuse me, companies in general, can lose reputation when they're not available, when customers can't buy what they want from them. So aside from just the retail part of this, or the revenue part of this, they've got issues with kind of their reputation, if you will. So the next reason why you would want to build a distributed application is latency. So for applications, latency really translates to performance. And that performance translates to a user experience. And that user experience itself also translates to money and loyalty, right? Now think about when you're online and using, say, a retailer or any online store or any online application. If the application or the site feels slow, you translate that as just poor performance, right? And that performance maybe translates into, well, they don't spend enough money on their applications. This actual latency issue actually costs money. So in, I don't know, this was about 12 years ago, Amazon did a study that said for every second page slowdown of just 1 second costs them $1.6 billion a year in sales. So for every 100 milliseconds that they're faster, that's an additional 1% in additional revenue. This study here that Walmart did is even more striking. So they found that for every 1 to 4 seconds that a page load time dropped, their conversion rates dropped with them. Right? So you can see just in 1 to 2 seconds, you go from high conversion rates to extremely low conversion rates within the applications. So who's heard of Cosmos DB? Yeah, who's used Cosmos DB? Okay, so I won't spend too much time on it. So Cosmos is Azure's horizontally petitioned, globally distributed database, right? So it's not a relational database, it's a NoSQL database. And not just NoSQL, but it's actually multi-model as well. So there's lots of different endpoints that Cosmos supports, including etcd. There's also a table API. We also have a Cassandra API, MongoDB, Gremlin for graph database, and then of course our own core SQL API. We also now have support for Spark as well, so being able to basically do online or analytics on your operational store. So being multi-model, we support different database types underneath, so key value, column, document format, and graph. And some of the key things to keep in mind is really for a database in Azure, we're the only one that offers an SLA on latency, and then also the only one that offers 5 nines availability. So that's enough of the sales pitch. I want to do some science with you guys here, so this is science time. Remember at the beginning of the talk, I wanted to talk about these 3 concepts. So consistency, latency, and availability. So these 3 concepts are absolutely critical to understand when designing distributed applications. So the rest of this talk, I'm going to go into each of these things. Now, when I talk about consistency, who's familiar with this in terms of consistency? Right, everybody is, right? So this is ACID, right? And in the context of a transaction for a relational database, you would say you're ACID. But for distributed databases, with consistency, this isn't actually what we mean. Consistency in a distributed data store essentially means the uniformity of data by replicas that's separated by hundreds or even thousands of miles. Does that make sense? So that's what we mean when we say consistency. It's not in the context of a begin transaction and do something and then commit or rollback. This is what we mean with say, consistency. So in 1998, a computer scientist by the name of Eric Brewer devised something that eventually became known as the CAP theorem. And what CAP theorem states is that for a distributed data store, you cannot provide more than 2 out of the 3 guarantees. Consistency, so I always get the most recent write for that database, or I get an error. Consistency. Availability. Every request that I send to that data store receives a response, even if it's not the latest data. And then partition tolerance. And that essentially means that the system or the data store will continue to work even if the connectivity is lost between the replicas. So to kind of put that in more of a graphical sense, there's kind of a decision tree here, right? So if I have a partition, a network partition, so a cut, network loss between one or more replicas within that database, I have to choose between 2 things. I have to choose between availability for that system, or I have to choose between consistency. So let me illustrate this a little better. So I have, I'm going to choose availability in this scenario, right? And I have a master database, and then I have a replica over here. So I'm going to write some data to it. So let's say I write 5 to the database here, and then that replicates. So all good, right? Everything's working. Now, if I have a network partition or a cut between the master and my replica in this scenario, and I'm choosing availability, if I write data on the master, what am I going to read on the replica, right? So I have to return something, even if it's not the latest data, because I'm choosing availability, right? So this is an active choice you have to make when you're designing a distributed system with a distributed data store, is a choice here between availability, right? I'm going to return something, even if it's not the latest data, or consistency, right? So let's show consistency now, right? So same setup, master and a replica, and I'm going to write 5 over on the master, and then that's going to replicate and become 5 over there. That's great when the network is there and everything's working. But if I cut that network connection between those 2, and then I write another piece of data, I get an error, right? I can't replicate. I can't maintain consistency between the entire system, so I cannot accept any more data. So that's what's meant with CAP theorem in terms of the availability or the consistency between these 2 replicated data stores. Okay? So CAP theorem does a good job of explaining what happens when there's a network partition between one or more replicas in a distributed data store. However, it doesn't explain everything that happens, even when the network is still running. So in 2010, someone postulated this, which became known as PAC-LC theorem. So what this is CAP theorem, but with some other conditions. So that reads, in the case of a partition of a distributed system, one has to choose between A, availability, or C, consistency. But even when the system is running normally, you still have to make a choice, and that's between latency and consistency. So what does that look like? So let's just put up our kind of decision tree. So CAP theorem on the left-hand side, network partition, availability, or consistency. But even when the system's running fine, I still have to make a trade-off, a choice between consistency and latency, right? So let me demonstrate what that looks like. So same setup again. I'm going to choose consistency in this scenario, okay? So I'm going to write data over here. But then what has to happen? If I have a network that's fully functional, but I'm choosing consistency. So every read on that system must be consistent. It has to be the same data. So what does that mean? I can't take any more writes to that system until I've completely replicated, until it's completely consistent across all of the nodes in that system, right? So that's going to go replicate and then act back. And now I can take more writes. Let's choose latency. So what does that mean? So in a system where I'm choosing latency, that means I don't care if every read is going to be consistent across all of the nodes in this distributed store, right? It doesn't matter. I'm just going to write data, and then whatever they read over there is just whatever they read. Is that clear? Everybody understand? Okay, we're going to do some demos around this just to show. So that's the science part out of the way, all right? So let's talk about each of these in more detail. I'm going to talk about read latency in here, right? So the idea, latency, the lower the latency for your application, the better the performance and the better your experience is going to be, right? Or the people using your application. So in this demo here, I'm going to show read latency. This is a single region database versus multi-region where I'm replicating it. Here, let me illustrate. So what I've got is I have a master database. This thing is set up in East US 2 is where this thing runs. And I have a web front end that sits on top of that in the same region. Okay. Now, as developers are wanting to do, they want to maybe distribute their front end in multiple regions to get that closer to the user, right? Because the closer it is to the user, the lower the latency is, right? You see this frequently. They'll use a CDN or something and then push all of their assets as far as they can closest to the user. That works great if your application is just a bunch of static pages, but in an application where you've got a database, that may be not the right thing to do. So this is what I'm going to show you is reads from a database that sit all the way across the US. It's about, I don't know, 2,600 miles. So what is that? About 3,700 kilometers across the US. And then I'm going to show multi-region and the difference in read latency there. So in this case, I've got a master in East US 2 and then a read replica set up in West US 2. Okay, let's go to demos. Okay, so this VM, this application, is sitting in West US 2. And I'm going to show the latency, read latency, for a single region database that's all the way across the US in East US 2 versus a multi-region database where I've got a master in East US 2 and a read replica in West US 2. Now I'm going to test 100 reads against this single region database from East US and West US. Who thinks this is going to be fast? Just want to ask. Nobody. Who thinks it's going to be slow? Maybe I'll see more hands. Who doesn't know what I'm talking about? Okay. And roughly about 60, 70 milliseconds. Not that fast, actually. 73 milliseconds. Now I'm going to try it against a multi-region database. So this is now a master in East US 2 and a read replica in West US 2 where I'm reading from West US 2. Who thinks this is going to be fast? You can't answer, Magnus. Okay. Who thinks it's going to be slow or slower? No? Okay, good. Super fast. And that was kind of weird how it screen refreshed there. Average latency, 4 milliseconds. Why? Because I'm only just probably a few racks away from where that data is actually sitting, right? So I've replicated it right up close to where my application is sitting, right? Closer to my user. So there's a difference. 74 milliseconds, 73 milliseconds versus 4 milliseconds for a multi-region. Okay, back to slides. So that's read latency, right? And the power of replicating that data closer to the application where you're going to be running it, right? So, and this is fine for applications where you're just reading data, but most applications need you to write data as well, right? So you have to worry about write latency in this scenario, right? So with Cosmos, last year at Ignite, so about September last year, we announced availability for a feature called Multi-Master. And what Multi-Master does is this makes every read replica you have now fully writable. And the benefit of this is now every replica, every node in your distributed data store can now get really low write latency in addition to the read latency you're going to get for this. This is going to increase your availability. Some of the side benefits of this is if I have an application where I need to ingest a large quantity of data, so maybe an IoT scenario or some kind of telemetry store, now what I can do with something like a multi-master capability is I can deploy it into just more regions and then do DNS load balancing across all of them, right? So I can now just add regions to add more write scalability, add more throughput to my applications. And then, of course, when you're writing to multiple nodes, you need to be able to resolve conflicts. So there's built-in conflict resolution with this feature as well. I won't spend too much time on this, but if you want to create a multi-master account, you could go into the portal and do this, or you can use an ARM template, create the account, and then just simply add regions within the account, within the Azure portal. In your applications, it's actually pretty simple to use. You don't change anything within your code except for a connection policy in there that says make this region or this client multi-master enabled. And then you just set the current region where your application is deployed. So functionally, your deployment is exactly the same with the exception of just what region you're going into. So you could just put that in a config file and then just spin that for each region you're going to be in. So extremely easy to set up and use within your applications. So let's do some more demos. So now I'm going to show write latency for a single region writing, a single master database versus a multi-write or a multi-master database. So here's kind of a map of what that looks like. So kind of the same setup before, right? I have a database in master node in East US 2 with a read replica in West US 2, and then 2 front ends on top of that. We're going to test it from West US 2. So this will be a single region write. So what's going to happen is all my writes from West US are going to go all the way across that entire country and then come back again. Versus multi-region write. So now what I do is I just write to my local node, right, my local replica, and then Cosmos will take care of all the replication on the back end. Okay, well, let's go to demos. Okay. I'm going to test latency for a single master versus multi-master database. So let's test 100 reads. This is the test we did before, right? Super fast, right? Because I'm replicating to that same region where I'm doing the reads from. Now let's test 100 writes. Who thinks this is going to be fast? Who thinks this is going to be slow? Come on, raise your hand. You guys are shy. This is really slow. So that's insanely slow. There must be something wrong with the WAN today. 234 milliseconds. That's really slow. I don't have enough filler in my talk here to fill up all the time it's going to take for all these writes. We'll just let that run. No, this is just single insert, probably about, I'm going to say 100K of data, each one of them. So it's very small payload in there. Yeah, that's really crazy. 236 milliseconds, very slow. Okay, now I'm going to do 100 reads from a multi-master account. That's, of course, going to be fast, right? Because we already showed that in a single master database or a single master configuration, it's going to be fast when I'm local. Now let's test 100 writes against that multi-master database. And fast, right? Average 6 millisecond, right? So super, super fast. Oh, I like that, putting that down. That's better. Okay, so there's kind of your test results, right? Writing to a database where you can write locally or just as if it's local and then have it replicated behind the scenes is going to make your applications much, much faster, much more responsive, right? You don't have to take care of any of that replication behind there. Okay, back to slides. So that is latency kind of rolled up. So that's the first concept, is the latency. Now I want to talk about consistency. And consistency, at least within Cosmos, you've got 5 different models you can choose from. Most other databases, NoSQL stores or horizontally partitioned databases that are in the market, generally don't provide this. It's either strong consistency or eventual consistency, or strong and bounded staleness. There's 5 you can choose from within here, so I'll kind of go through each of them. Strong consistency is, as you might expect, means that everything in the data store, distributed data store, is completely consistent all the time, right? So when I showed you optimizing around consistency earlier with that writes and with that illustration, that's strong consistency right there, right? So I cannot take any more writes until everything is replicated and consistent across the entire store. Bounded staleness, this is more of a relaxed level of consistency, and essentially what it means is stale reads are okay up to a certain amount of time or after a certain number of updates. So bounded staleness is defined as a period of time or as a number of updates that it can lag behind within the distributed data store. Session level consistency, this is unique to Cosmos. Essentially what that means is for my application client, everything is strongly consistent within that region, right? So essentially it's in region strong, and everything you write, you can read. So read your own writes within there. Consistent prefix, more relaxed level of consistency. What that means is everything will be consistent at some point, and all of the updates you see will be in a consistent order. So the prefix of the updates will be in order. And then eventual consistency, as the name kind of implies. Everything will eventually be consistent. There's no guarantees around when it'll be consistent, and there's no guarantees in the order in which those writes are able to be read within the store. Another concept around consistency I want to talk about is this relationship of latency and consistency. There's a direct relationship between these two things. And it's actually more pronounced the greater the distance between the nodes in your distributed data store. So things like the speed of light actually become a factor in a distributed store when you're talking about hundreds or thousands of miles. Packets, right, nothing travels faster than the speed of light, including packets. On a WAN, they're actually going to travel quite a bit slower because they've got lots of equipment they need to go through, right? There's switchers and routers and all kinds of things, and you can have lossy links, retries, all of this stuff. So WANs are, typically about 10 to 15% slower than you would find for, just raw speed of light. Another concept or topic I want to talk about is consistency versus throughput. Now, this is unique to Cosmos in how we do writes and reads within there. Every write within Cosmos goes to a replica set. And within a replica set, there's 4 individual copies of your data that's in there. Now, there's going to be a leader, and then there's 3 followers, and then one of those followers is actually also a forwarder, and its job is to replicate data to other regions that you have configured. Within Cosmos, when you write data, we do what's called a quorum write. For strong consistency, this is a global majority, right? So when I was showing you earlier, when you're doing optimizing for consistency in your store, what global majority means is that I've now got data committed in every one of my replicas, right? For any of the more relaxed levels of consistency, so bounded staleness, session, consistent prefix, and eventual, everything is a local majority. So that looks like this. So I have to commit to 3 of the 4 replicas within that replica set before I can ack it back to the client. And that has to happen in less than 10 milliseconds, by the way. On reads, slightly different. So reads are either a local minority, a single replica for a relaxed level of consistency, or they're going to be a local minority for a stronger level of consistency. And the reason that is that's how you provide consistency within the replica set, right? So I need to read from more than one replica, and they need to match in there. If they don't match, what happens is we'll take the read with the higher LSN because that's the more recent write within there, right? So these are monotonically increasing these log sequence numbers that all of your writes are done or committed to within Cosmos. So if there's 2 in there and they don't match, the higher one is the later one in there. So this is important to understand. When you use a higher level of consistency within your application, you functionally get half the throughput for that database, right? Because it's going to cost you 2 compute operations. 2 replicas have to be read to return your data. Okay, so more demos. I'm going to do 2 pieces of this demo. One is going to be consistency versus latency in there, and then I'm going to show consistency versus throughput. Now let me illustrate this. So in my first demo, consistency versus latency, I have 2 databases. And this one is eventual consistent, so I'm using the weakest level of consistency, and I'm replicating it. It's about 1,600 kilometers. So from West US 2 to the central US region, which is somewhere in a cornfield in Iowa. The next one is same setup, so same 2 regions. This account is configured for strong consistency and replicating 1,600 kilometers from West US 2 to central US. I'm then going to show you what happens with the speed of light for these types of systems, where I'm going to show you replication for an account that's strongly consistent, but now double the distance. So instead of 1,600 kilometers, I'm now 3,200 kilometers all the way across the US. Okay? And then for my consistency versus throughput demo, I'm going to show you what the cost is for doing 100 reads for eventual, and then 100 reads for strong. All right, let's go back to demos. Okay, so consistency versus latency. So I'm going to test 100 writes in West US 2, eventual consistency level. So I'm replicating, the account is set up, 2 replicas, West US 2, Central US, eventual consistency. And my replica 1,000, 1,600 kilometers away. Super fast. Why? Because I don't care if my reads are consistent within this database. I'm using eventual consistency, right? Now let's test it with strong consistency. Who thinks this is slower? Awesome, you guys are listening. I love it. It means you understand me, actually, even better. Slower, right? 67, 62 milliseconds, right? What's happening? So I'm writing my data in West US 2. I'm replicating it 1,600 kilometers away and then acking it back. So I have a round trip time of 3,200 kilometers for that write, one write. And that's 63 milliseconds. Let's test 100 writes in West US 2 with strong consistency, and now double the distance. Just yell out, who thinks, how much slower is this going to be if I'm double the distance? 5 times slower? 4 times? Double the distance, double the latency. It's a direct relationship between the two. Cool? You guys like these demos? Yeah? I'm going to show you where to get them after we're done. Here's 100 reads, eventual consistency in West US 2. So I'm reading from a single replica, 1 unit of compute. In Cosmos, how you measure compute or throughput is called an RU, a request unit. And it's essentially a proxy for some compute, so some CPU, some memory, and I/O, right? And generally, 1 KB read, point read in Cosmos, in partition read is 1 RU. So these reads are going to be a single RU because I'm just reading from a single replica, right? But if I'm going to read from that account that has strong consistency, I have to read against 2 replicas. So it's 2 RU, right? So I have half the throughput now. If I have 1,000 RU provisioned for that database, I can only get really 500 RU out of it because every read is going to take 2 request units to do. Okay, so back to slides. Okay, last topic is availability. Now, anyone that's ever built anything or drawn on a whiteboard, their distributed system has drawn something that looks something like this, right? So I've got my IoT device, my browser client, my mobile phone, and it's going to connect over the internet, which is colloquially shown as a cloud. I'm then going to need to load balance this because I'm designing for availability, right? So I don't want it to run in a single region, or I'm designing for latency as well, right? So I want to get closer to the user. So I'm going to use a DNS load balancer, and then I'm going to have something like an application gateway or some kind of load balancing at the front end. And then within the region, I'm going to have multiple tiers of this application, and then within each tier, I need to have redundancy, so I'm going to have multiple VMs or, I don't know, multiple instances of whatever my front end is going to be, and then I'm going to load balance those requests over my middle tier, and I'm going to have multiple instances of that. And then on the back end, you may have a SQL in your thing. Well, that would be a poor choice. You should use a Cosmos DB because Cosmos DB is going to provide you the ability to replicate your data across all of those regions within there. And then, of course, within the region itself, and I showed this earlier, you've also got redundancy in region as well, right? So there's 4 copies of your data within Cosmos in there. And then if any of those replicas fall down, you're still up, right? Because you still have 3 of them in there. So you can still do writes, right? Because we require 3 replicas on a write. And you can certainly still do reads, single replica read or even bounded, staleness, or strong reads in there. So you're still going to have availability within there. And if a region falls down, right, no problems as well, right? Because I'm actively replicating my data. Traffic Manager just will redirect all my requests to my other region until that region comes back. Clear? Who understands or knows what RPO is? Can someone define that for me? Yeah? You know, can you spell out what RPO is? Yeah. And what about RTO? Who knows what that one is? Same guy. Okay. Recurring time objective. Right. So here's how I like to illustrate it. You're absolutely right. So RPO, another way of saying that is how long did you lose data? Right? That's your recovery point objective. And then RTO is how long are you down for? This illustration here is a great way of looking at it, right? So RPO and RTO are just a function of time, right? RPO, how much time that represents the data you lost, right? This could be a backup or something that gives you your data back. And then RTO is how hard your team working to get your site back up, right, within there. So these are important, actually, to understand when you're designing a distributed system because they have a direct corollary to the stuff I've been talking about, actually. Within Cosmos, we actually publish an RPO and an RTO for the service. So if you are running Cosmos in a single region, in either single master, multi-master, doesn't matter which, any level of consistency, but I'm only running single region, your RPO is about 4 hours, right? Because that's the amount of time between snapshots that you can by default get in Cosmos. But your RTO, we don't guarantee anything, you know, maybe up to a week to get your data back, right? So if you're running or wanting to create a mission critical application that's got high availability, right? 5 nines or whatever availability, you would never run anything in a single region. In fact, if you're creating anything that's mission critical or requires high availability, you would never run a single instance of anything, right? You would have to have multiple instances of that thing because VMs fail, right? Things fall down, right? It's a cloud, right? It's running on commodity hardware. So you have to run multiple regions. So multiple regions running a single master, say a relaxed level of consistency in there, RPO, 15 minutes, less than 15 minutes. Why is that? Because that's the maximum amount of time, 15 minutes, and it's generally in the seconds or milliseconds range that it takes to replicate your data from one node to another. So once you do a write and that data is replicated, you now have data durability within there. So your RPO is going to be pretty low. And your RTO is going to be about 15 minutes. That's the amount of time from when we recognize that a region has failed to when we fail over your account. If it's a single master and you have a read replica, right, because you're running multiple regions, that will promote that other region, your read replica, to become the new master, right? And that RTO is about 15 minutes. In a multi-master configuration, you're going to get the same RPO for that relaxed level of consistency, right? Whatever time it takes to replicate that data to another region, that's going to give you data durability in the case of a disaster. But your RTO is 0. And the reason is within Cosmos, when you use the Cosmos client, if we detect a region has failed, we'll just fail over your application automatically and then send the writes to the next region. So you have 0 downtime in your application. You won't lose anything. And then for bounded staleness, you've got KNT. That's time or update. So when I explained bounded staleness earlier, that's your RPO for that. And then for multi-master strong, you actually can't do this. We actually allowed customers to create this, but this doesn't make any sense, frankly, because if you're strong consistency, With multi-master, you have to replicate all your data everywhere. So your latency is pretty much the same as if it was just a single master database. So we don't offer this anymore. So thinking about RPO, the data durability, and then RTO, can you translate that into this? Right? So if I fall down, what does consistency mean? What am I optimizing for? Which one? Am I optimizing for RPO or RTO? RPO, right. I need consistency. It's data durability, right? So if I have an insanely low RPO, maybe it's RPO 0, I can't lose any data at all, then I need to be strongly consistent. What if I need an RTO 0? What am I optimizing for there? Availability, right? So if I need an RTO 0 or close to it, then I can't be strongly consistent. You can't have both of these things at the same time. CAP theorem says you can't have RPO 0 and RTO 0. It's physically impossible in the universe to do it, right? And we've proven this out. Cool. Let's talk about conflicts. How am I doing on time? Good? Okay. 20 minutes? Awesome. All right. In Cosmos, so if you've got a multi-master database and you've got multiple nodes that can take writes, conflicts can happen, right? This can happen in any kind of system where you can have writes at any point. They need to be able to merge, and you need to be able to resolve conflicts. Within Cosmos, there's 3 ways you can do this. You can use last writer wins, which, as the name kind of implies, just means that you write it. The second, here I'll just go through them quickly, is you can write a custom stored procedure within Cosmos. Stored procs in Cosmos are functionally JavaScript, and they're all scoped to a partition key. And then the third way is you don't do any conflict resolution at all. We'll just write all conflicts to a conflict feed. You can read from that and then process those however you want. So let me kind of quickly go through these. So in last writer wins, this is essentially the default, and it's applicable for any of the APIs in there. So if you're using Mongo API, Cassandra API, Gremlin API, SQL API, all use this _TS. It's essentially an epic Unix timestamp for resolving conflicts. And as the name implies, the last one there is the guy that's going to be the winner. In our SQL API, you can also make this a numeric property. So let's say if you've got two customers in here, I've got Scott and Satya, and they're both coming in. The one with the higher user-defined ID is going to win the conflict, right? So this assumes that they have the same ID for the property. I didn't show that there. With a custom merge procedure, this is essentially just a stored proc. You have to write it. It has to have a special signature in there, and then you register that with the container. Like I said, all stored procs within Cosmos are scoped to a partition key. So this may be unusual for people that aren't used to horizontally partitioned databases. Stored procs in SQL Server, you can pretty much talk to the entire planet, and you can also do unnatural things like write C code and put them in there. I think still, no? Did we kill that feature? I don't know. Years ago, you used to be able to write C in stored procs and then run them and then break all kinds of things. No more, thank God. So these are scoped to a single partition key. So anything within Cosmos, you have to think in terms of partitions, logical partitions. Including these. Exactly once guarantee, so we'll run it, promise you, exactly one time. And it's executed as part of the commit that happens in there. If you have an error that gets thrown inside of here, we will just write the conflict to your conflict feed. And this is only available for our SQL API. And then the last way is the conflict feed itself. Basically, this is no conflict resolution. There's a special feed within Cosmos. You can create a client that reads that, processes conflicts, and you can do whatever you want with them. You can update whatever record does get committed, because when you have a conflict, something will get committed inside there. So you could either replace that with what's in the conflict feed, or update it, or do whatever you want to with it within there. So, and then that's kind of what it looks like in there. So you just read from the conflict feed, and then just go through through all of them in there. You can process them any way you want within there. Let's show conflict resolution. We're going to generate some conflicts, and then I'll show you how to resolve them. Okay, so number 4. So this demo here, I'm going to generate insert conflicts on a container, and I'm going to use the last writer wins policy. This is going to be whichever one has the higher max user-defined ID is going to be the winner. So here's some inserts. Attempting to insert. Oh, okay, didn't get it. Okay, I got a conflict. So here I've got Sydney McClure. Oh, let me set this up for you. This demo here, I've got is a multi-master database. I have a replica at East US2, one in West US2, and a third one in North Europe. I have an application that's written that has all three connections to all three of these, and I am simultaneously trying to generate writes or generating writes simultaneously on three different threads to generate conflicts within here. Okay, so that's the setup. So I've got three in here. So user-defined ID 514, 178, and then 939. Oh, you know what I forgot to do? I forgot to set this thing up. Hold on. And just a second, I got to pull open the portal here. And where are you? Okay. What is up with that? Okay. That's not good. I have to update my firewall settings, huh? Let's see if I can outsmart this thing. It's our internal security team getting crafty again with our stuff. Why can't I do that? Now I can't VPN in. This is odd. Huh, okay. Demo's not working. So we will not do a demo on that. Well, actually, I'll just fake it and say, so in this one here, 939 was the guy that won. So, and then doing a second one, I'm going to use a user-defined procedure. This one would use the minimum of the user-defined ID, and that would be the winner. So try to do some inserts here. Now I'm getting some weird latency on this thing here. You mean after it's been committed? Oh, wow, here, look at this. Okay, looks like I'm having some issues with connectivity. Yeah, the conflict resolution will still happen within the 10 millisecond SLA. It's executed as part of the commit itself. So, yeah. Let's try. Okay, so is it working? Okay, this demo is acting weird. So let's go back to slides. So that was my attempt at showing you conflict resolution within multi-master. I guarantee you it works. But let's move on to another topic. So we talked about this relationship between latency and consistency within a distributed application. There's actually kind of a trick you can use to kind of cheat this a bit. We talked about, so when you have to commit data and you have a strong level of consistency, so I have a very low RPO for this application. In a system where you've got to replicate that data thousands and thousands of miles, this can introduce a level of latency that's generally not well liked by most applications that like speedy performance. And you can actually kind of cheat this. And the way to do it is to create region pairs within Cosmos, use a lower level of consistency across the entire application, and then basically create these region pairs where I'm going to essentially commit it into 2 regions simultaneously so that I have greater data durability. So the idea here is I'd have an application, say I'd have 2 in West US and West US 2, and then another pair in East US and East US 2. And the idea is to keep the region pairs very close because I'm going to commit it and make it durable in a second region, and I have to do that on every single write. So let me show you another demo here that shows you this, assuming that everything kind of works. Okay, so here's this setup with custom synchronization I'm going to show you. So I'm going to show you, there's 100 writes in West US 2, strong consistency, and this is between all the replicas I've got within there. It's not. What happened? Oh, sorry. Weird. Now can you see it? Okay. So 100 writes, West US 2 session, excuse me, that's session level consistency. This thing is going too fast. Hold on. What is going on with this? I'm having connectivity issues. Start. Don't use the public one. Okay. 100 writes, West US 2, strong consistency. So this is going to be slow, right? Because I've got to replicate it all the way across the United States. So I think this is, whatever, 2,000 miles, 3,200 kilometers. Okay, so 100, here, let me make this bigger. Okay, about 100. Now, session level consistency with all of my replicas. However, I've got a region pair set up from West US to West US 2, so not very far from each other. And my consistency is much, much less. Right? So what I'm doing is I'm doing a write into West US and then immediately issuing a read for that same data. And let me show you how I do it. Let me empty this. So within my application, I've got 2 things going on here. I've got a read client, or I've got a write client. This is writing to West US 2, and then I've got a read client that's reading from West US. So when I set up a connection policy here, here's my write policy, and I'm using multi-master here. And then setting it to West, then the second one to West US, and then this is to West US 2. And then here's my read policy here, and that read location is West US. All right, and then I just new these up and then open them. And then this is the trick. For every write I do within the application, in my response object, I'm going to take the session token that comes back. This functionally is the LSN for the write that happened. And then I'm going to issue a point read for that same piece of data and flow the session token, the LSN. So essentially this tells Cosmos, go pull that, replicate that data, and do it fast. So that's how we trick it into basically creating strong consistency in an account that has a weaker level of consistency. right? Within Cosmos, you could weaken your consistency level within an application. So you could define it as, say, strong or bound staleness or session, and then within your application itself, or even on every request, lower that consistency. But what you can't do is create a stronger level of consistency within that account. But you can do something like this, and that'll give you higher data durability. Now, this is kind of costly, or can be, right? Because you need region pairs for your application in every region where you want to be able to serve up data. But this will help with reducing that latency, giving you higher RPO within your application. Okay? All right, back to slides. So that's pretty much all I wanted to show you, except for this. So all those demos I showed you are actually all on GitHub. So is this showing? No, of course. Right here. So Mark J. Brown, that's my GitHub handle, Global Distribution Demos. And this will walk you through all the benchmarks I showed in my test, or in my talk. And I wrote an ARM template that deploys the entire thing. So the only thing you need to do is create a VM, make it a beefy one because you're going to want to run Visual Studio on it. There's a data science VM that we've got right here in the gallery. You can just provision this thing. That's pretty big. And then run your ARM template. I'm also the ARM guy, or I'm the control plane PM as well, in addition to all the multi-master stuff I do. So I wrote this template. But this will easily create all of the Cosmos accounts, configure them for the consistency levels. These are all, unfortunately, hard-coded within US regions, except for one of them that's in Northern Europe. But it'll allow you to show how this works, and you can use this as the basis for benchmarking your own applications within there. One thing I will call out is run the initialize and the cleanup in here. So within the application, and I'll do this right now, when you provision these accounts, you're not paying for anything within Cosmos. That doesn't happen until containers get created, so don't worry about the cost of that. However, before you run any of these things, you need to run initialize on here, and then when you're done, definitely run cleanup, because that's going to delete all of the databases and containers, and then it won't cost you anything. And then you should probably stop the VM as well. Anyway, just wanted to give you some pointers there for running this thing if you wanted to check it out. So that's it for me. I'm all done. If there's any questions, I can take them, and I have some Cosmos DB stickers.
Nice.
Which are very nice.
That was the first question. Any questions? Yes, there's a question right over there.
Yep. Yeah, so multi-writes are going to be, it's basically N+1 within there, so they're double the cost. Because you're going to pay for every single region that you're replicating to. We're single master. We don't price that way, but for multi-master we do. So it's double the cost. Yep. You want a sticker?
More questions?
You get a sticker. All right. There you go.
This is.
Yeah.
Oh no, not you. Well, okay then you.
Okay, so I have a tricky one. So your demo.
No, we're not doing it for Azure Stack.
Aww. That was my follow-up question.
Okay.
The demo you were doing, where you were doing the custom rules, your custom sync rules.
Mm-hmm.
So you were forcing a higher RPO, fine. But am I right in understanding that if I've set that lower level of consistency, that implicit in that my SLA is lower?
No. So you're going to get latency SLA except for strong, right? Because we can't guarantee single-digit latency, write latency, when you're replicating hundreds or thousands of miles.
Yeah, because it doesn't work like that.
It doesn't because of cap theorem, right? Well, actually, Lc Theorem in this case, right?
Yeah.
So, yeah.
All right.
You shouldn't really run. I've seen very few customers who actually absolutely have to have strong consistency, especially for an application where they're replicating it hundreds of
You're
thousands
standing
of miles.
right there. You have a PowerShell logo right in your forehead. It's perfect.
Oh, I have a PowerShell logo on my head? Oh, that's terrible. I'm a CLI guy. Oh.
All right. Additional questions? All right. Let's take. Thank you, Mark. Thank you very much.
Thank you very much. Thank you, everyone.